Welcome back, Physics 11, to a brief video on the force of friction. So in the previous week, we looked at the three laws, so Newton's three laws. First one being objects in motion remain in motion, objects at rest remain at rest unless acted upon by an outside force. Number two being most commonly shown as the formula F equals ma. And number three, for every action, there's an equal and opposite reaction. So in our first video here, talking about a specific type of force, it is important that we keep in mind that those three Newton's laws are really our driving force in terms of helping us understand the material. The only difference is now that when we're looking at Newton's second law, we're going to be applying specific types of forces, which we'll see have their own formulas in many cases. So the first thing I just want to say is that our force of friction is created whenever two objects are in direct contact. Okay, and on the microscopic level, what's essentially happening is irregularities on the surfaces catch on each other. So for example, if we have surface number one, we've got all these spiky points on it. Surface number two has a number of its own spiky points on it, and you can see that somewhere at some point, some of these will come in contact with each other. So that's really what we're seeing on the microscopic level. One piece is trying to move this way and one piece is trying to move this way. Those little bits are going to catch on each other, and that's what really creates the friction that we're seeing. Now, in terms of friction, it does have its own force, which is probably not a surprise, and that is as follows. Ff, which is the force of friction, is mu times our normal force. So normal force is what Fn stands for. It is always perpendicular, meaning it's at 90 degrees. It's given by this symbol. So it's perpendicular to the surface. And when we're looking at, let's use a better color than this one, let's go with dark blue. When we're talking about mu, this symbol here is the Greek letter mu. It's the Greek letter m. It is called the coefficient of friction, and it is a unitless quantity. We can see why it would be unitless. If we rearrange this formula over here, we're going to have mu equals the force of friction divided by the normal force. This is going to be measured in newtons per newton, and so that would be canceled out. And essentially, this is the one way that we can look at what mu is. It's the ratio of how much friction force we're going to get for every amount of normal force. So the higher the coefficient, that means the more friction force we're going to get per unit of normal force. And in terms of the mu, it also depends only on the types of surfaces. Okay, so between, for example, rubber and wet pavement or rubber and dry pavement, those would have two different coefficients of friction. Obviously, between rubber and dry pavement, we can assume it would be a higher coefficient of friction because you can stop better on a dry road than a wet road. Now, this brings us to a couple of quick definitions here. So static friction, static always means stationary or not moving. So this is the friction between stationary objects. And kinetic friction is, you guessed it, friction between moving objects. And in general, the force of friction, that is the static force of friction, is always going to be greater than the kinetic force of friction, and therefore the mu static will be also greater than the mu kinetic. Now, what I want to give as an example of that is, let's assume for a moment that I've got a piece of wood here, I've got a block resting on top of it. Now, right now, there's not going to be any force of friction, but if, for example, I chose to lift this end of the board up here, then all of a sudden we would see the board starting to tilt over, and at some point eventually this block would start to slide. So up until it starts to slide, the force of friction there is going to be equal to whatever force is pushing it. And so even if this was still a stationary object, if I was applying a force to the left, well, as I apply more and more applied force, the friction force is going to get bigger and bigger and bigger. But those two forces are going to match up until the point where it is static. So up until the point where it starts to slip. So the friction force will always be equal to the applied force, in this case, when it's still static, for the simple reason that we know that it's not accelerating, therefore those two have to be equal. But once it starts to slide, so let's say I'm pushing this along here, and I keep increasing my applied force, well, once I get the force big enough so that the static force of friction can no longer keep up with it, that's when it's going to start to slip. And all of a sudden, this force of friction, which up until a moment ago, up until it started to slide, those two were going to be equal. But once I've made this static friction force, or once I've made the applied force, sorry, just a tiny bit bigger, then at that point, the force of friction goes from the static force to the kinetic force, which is actually much smaller. So you can see what the result is, that once it starts to slip, it will accelerate quite quickly. So we'll go from stationary, and all of a sudden that force of friction becomes much smaller instantaneously once it starts moving, and so we'll get a larger acceleration. Okay, so let's try a few practice problems here. The first one, I will show you an example of how this would be done, and the next two, you can please pause the video and try it for yourself. So the first thing we should always do, of course, is draw our free body diagram. I think I have a bit vague here. Let's make it a bit smaller. Force of friction, first thing we do, like I said before, we draw a free body diagram. And so we've got the normal force and the gravitational force, and these two are going to be equal. Now, we want to find the force of friction. This is question A. So we know that there is going to be an applied force. It's being pushed along here with a force of 45 newtons. And we don't know what this force of friction here is going to be. But we do know that it seems like it's going to be accelerating. So what is the force of friction? Well, we go back to our previous formula, which is, and over here, we go to the formula, which is the force of friction equals mu times the normal force. In this case here, we don't know what the normal force is, but we do know what the force of gravity is. And this is where our diagrams are going to come in handy quite a bit when we're trying to solve these types of problems. So we don't have a formula for the normal force, but we do have a formula for the force of gravity. And so let's take a little detour over here. Force of gravity equals m times b. In this case, this is going to be 3.75 times 9.8, and that amounts to 36.75 newtons. So that's what this Fg here is, 36.75 newtons, and by extension, we know that this also is going to be 36.75 newtons because it's not accelerating upwards, therefore upward and downward forces are going to be equal and opposite. Okay, carrying on with that, so force of friction is mu times normal force, so that means force of friction equals mu is 0.65 times our normal force, which is 36.75, and that gives us a total of 23.9. So 23.9 newtons, that is our force of friction. So now if we're trying to solve for part B, I'm going to change the pen color here. Let's go with, we'll just go with black. Okay, so find the acceleration. In this case here, we can always rely on this formula here. So our net force is equal to our mass times acceleration, but it's also equal to the sum of the forces acting on it. Now, I could include the normal force and the gravitational force and the friction force and the applied force, but we know that the normal force and gravitational force, they're going to cancel each other out, so we don't care too much about them for the purposes of this question. So in this case here, I'm just going to say it's going to be the applied force plus the force of friction. Those are the two forces involved in determining the acceleration. And so applied force we know is going to be 45. So let's go back to our values here. So 3.75 times the acceleration is going to be our applied force, which in this case is going to be 45, and we're going to add in our force of friction. Now this is where there's a potential for making a mistake on the equation here. We've just determined that this force of friction here is equal to 23.9 newtons. But we do have to be careful about the direction. So if we're thinking about the direction here, we know it's in the opposite direction of the applied force. And so if the applied force is 45, then this is going to be negative 23.9. So our mass times acceleration equals our total force here. So this is going to be, if we add 45 and negative 23.9, we're going to have 3.75 times A equals 21.1 newtons. And again, we're just doing some algebra now. So 3.75 divided by 3.75 on both sides. And we have our acceleration of 5.6. So A equals 5.6. That's going to be meters per second square. And then up here we had our other answer, F equals 23.9. Okay, so please pause the video here and try out the next two questions on your own. And then once you've solved them, we'll come back and we'll finish these questions up. Okay, so I'm going to go ahead and give us our free body diagram here. Hopefully you have solved these on your own. We've got the normal force, the gravitational force. And because we know it's not accelerating up or down, we know those two must be equal. Now, it's being pushed along a sheet of ice with a force of 0.24 newtons. Okay, and this is going to be our applied force. Now, this is where there is something that you need to make sure that you're paying attention to, because this comes up quite often. In this question here, it says it moves at a constant velocity. Now, the fact that it moves at a constant velocity tells you that the acceleration is equal to 0. So constant velocity means no acceleration. So if we look at our free body diagram, we know it's not accelerating up or down, so the normal force and gravitational force must be equal to each other, but we also know it's not accelerating left or right. So if it's not accelerating left or right, then that must mean that by extension, the left and right forces are also balanced. And we can indicate different arrows that match each other. We can indicate with a different number of lines. So 2 lines on these arrow means these two, the applied force and the friction, are going to be equal to each other as well. Okay, coefficient of friction. So here we go. We know the applied force is equal to the force of friction in this case from our diagram. And this is equal to 0.240. And this is equal to our formula for force of friction, which is mu times the normal force. Now, we are trying to find mu, but we don't have a normal force just yet. And we also don't have a formula for the normal force. However, you'll notice that the same observation that applied last time applies to this case as well. We know that the normal force is equal to the gravitational force, which is equal to m times g, which is 0.200 times 9.8. And 0.2 times 9.8 is going to be 1.96. So equals 1.96 newtons. And so here's our formula. 0.240 equals mu times our normal force. This discovered was 1.96. And so we're going to divide both sides by 1.96. And we have a total of 0.122. So our coefficient of friction equals 0.122, and that is our final answer there. Now, lastly, for number 3, the free body diagram is a little bit trickier. We have to go back to one of the notes that I mentioned earlier about the normal force. So the normal force is always, like we said here, always perpendicular to the surface. And so the other thing I didn't mention before is that the force of friction is always parallel to the surface. And so that is an important point when we're trying to draw this diagram here. So if we try and finish up this diagram, we've got an upward force and a downward force. We've got the force that we pushed into the wall and the force that we pushed out of the wall. Now it's stationary, and so what this means is that these two forces will be balanced and these two forces would be balanced. And now we just have to identify what those forces are. So the downward force, as you may have guessed, is going to be gravity. The force that opposes that, and that force happens to be parallel to the surface, this is going to be our force of friction. Now this is going to be our applied force, and the normal force is always perpendicular to the surface, so that means that this is our normal force. And so we're just about ready to go. We're trying to solve for the normal force. Well, first of all, we're trying to solve for the force of friction. So we know this value here is 45, and so therefore we know this value here is also 45 newtons. That's what's listed here in the problem here. The applied force is 45 newtons, so therefore the normal force is going to be 45 newtons. Now the force of gravity here is going to be m times g, which is going to be 1.1 times 9.8, and that gives us a value of 10.78. And so that means that this is going to be 10.78. So just by looking at the diagram, we've already got quite a few bits of our information there. So let's look at the force. The force of friction is going to be, the value is 10.78, and this is equal to mu times the normal force, which we've already solved for, is 45. So again, we're going to take our 10.78, we're going to divide both sides by 45, and we have mu equals 0.24. So that is our final answer for the third example question. So try out the problems on your own for these ones. If you have any questions, please let me know. Come by during Fit Block. I'm happy to help you out. And all the best. Thank you.